All right, so today we're going to talk about the kinds of variables we'll be dealing with, um, and we'll talk about, give some definitions of some terms that are going to be really important. And then we'll get into, well, a little bit of stuff with temperature, and then we're going to spend some time talking about pressure, what pressure is, and how to do calculations with pressure, how to do pressure measurements. And then when we're done with that, we'll start talking about energy. So remember, there are four main principles that we're using in this class. Conservation of mass, conservation of energy, entropy always increases, and entropy is zero at absolute zero. Okay, so those are the four things, and we'll be getting into the energy balance. That's going to be the first one we're going to talk about. Before I get into new stuff, anybody have any questions about anything? Nice binders. I like the binders. Yeah, that's right. And so I'll be posting problems in the content section sort of at random. That doesn't mean they're assigned. When I assign them, it'll be in the announcements. So I'm just putting those up as I get them together. But look in the announcements for which ones you're supposed to work on. And yeah, if you notice, so I posted some problems, and I'll assign all of those or some of those to this class. And then I also posted some solutions. I think for this set, it was about half of the problems I posted solutions for. So one thing to keep in mind in this class is, so keep in mind, this class isn't going to be dealing with vectors for the most part. But the idea of direction comes from the signs of things, the plus minus signs of things. And so you can think of the signs of quantities as being, they are associated with direction. And keeping that straight, using the right sign convention is going to be a key to all of this stuff. And some of the sign conventions that we're going to use are going to be, they're sort of going to go against what you're used to, the sign conventions you're used to from Physics 1. Like, for example, in Physics 1, when you isolate a body, you draw your free body diagram, and then you calculate the work done on that body by a force. Positive work means energy is being added to that body, right? We're going to use the opposite of that in this class. So I'll just write it like this for now. The change in the energy of a system is equal to, that's the heat. And I think a lot of you, at least a lot of you, have never talked about heat yet. Minus the work. You have talked about work. And this, this idea is really simple. Like, the total change in energy is just the change in energy due to temperature gradients plus the change in energy due to application of forces. That's a simple idea. It looks more complicated than that because you have one positive and one negative. And the negative sign here is shows that positive work doesn't mean that the energy of the system is increasing. It means the system is adding energy to its surroundings. Okay, so it means the system is doing work on the surroundings. Okay, that seems like a weird choice. And if you think about work the way with the sign convention that you're used to from physics 1, you're going to get all these problems wrong. And you want to get some of them right. So, yeah, Q is heat. And we haven't talked about, we'll spend a lot of time talking about that. But just like work is energy, is a change in energy due to application of forces, heat is change in energy due to a temperature difference. Okay. So why do they choose this sign convention? If you think about it this way, it's easy to remember, and we'll talk about it more as we get into energy. But to keep this straight, think of a heat engine. Or let's think of the gas inside a heat engine. Think of that as the system. The idea is that you add energy to the gas by lighting a fire under it, or increasing the temperature of the gas. That adds energy to the system, and then that energy is taken out of the system by using that energy to power, run a train or whatever you use the engine for. Okay, so so you add energy to the gas by heating it. And energy is used to apply forces to the surroundings. So if you're thinking about a heat engine, Q and W are both positive. You know what I mean? Q is positive because you're adding energy to the gas, and W is positive because the gas is doing work on the surroundings. Okay, I'm spending too much time on that now, but that's something that's going to be coming down the pipe, and we have to be careful about keeping that straight. Okay, so let's talk about states, processes, properties, and processes. Okay, so a property is a single thing describing a system at a single instant. Okay, so what are some examples of properties? Volume, temperature, pressure, entropy, These are all things that have a defined value at a single snapshot in time. Okay. What else? Mass, density. So all of the variables that we deal with that describe a single instant in time, each one of those is a property. If you consider this is sort of a theoretical thing because there's infinitely many properties, you can describe things infinitely many ways, but if you take all of the properties that describe something at a single instant, that's called a state. The state is the collection of all the properties. That's just what's going on at that instant, you know. So that's all the properties of a system at a single instant. You know, so if we took a picture of the room right now, and then we'd go through and, you know, somebody's writing, so you could say the person writing is a property, and the person has dark hair, that's a property. And all of these properties are part of defining that person at that instant, and that's the state. A process is moving from one state to another state. So let's say the transition from one state to another. So notice that most of the equations we're going to deal with describe one of two things. So either relationships between properties at a single instant like, for example, PV equals nRT. Okay, that's saying at a single instant there's a relationship between pressure, volume, temperature, the number of moles you have. And the other possibility is that how these equations will describe how properties will change during a process. So now talking about properties, they can be either extensive or intensive. We're going to use both of these types And we're going to use the same equation in forms where the variables are intensive and the variables are extensive. So we want to be clear about what these mean. An intensive, yeah, so let's do intensive first. So an intensive property is a property that's given on a per unit basis and it has a definition at a single point. So some examples are density rho, which has units of kilograms per meters cubed. So this is given per unit because it's sort of it's a measure of mass for every unit of volume. And you can have the density of a material vary continuously as you go from one spot to another. Okay, so it's defined at a single instant. So think about, so density can be defined at a single instant. Mass is not defined at a single instant. Okay, like if you keep, so think of a piece of lead, and keep limiting in as you go smaller and smaller. As you do the limit down to zero size, you just go to zero mass. So it's not, and that's no matter what material is. So that's not a valid measure of anything at a single location. Okay, and that's why density is an intensive property, but mass is not. And we'll see mass as an extensive property. Another intensive property is temperature. I'll always write that as a fancy T with little shoes and tails. So temperature, it's pretty clear if you look at, well, you can use, lots of different units for temperature, let's say Kelvin. Density is pretty clear from looking at the units that that's on a per unit basis. We're dividing the mass by the volume. Temperature, it's not so obviously clear, but you might remember from Physics 1, if you got to any of this stuff towards the end, that temperature is that from the temperature, you can calculate the average kinetic energy of a molecule. I don't know how many of you got to that in Physics 1. But so in a sense, temperature is like a measurement per molecule, per particle. Okay. Pressure is another one. So I'll write that with a lowercase p, and SI units for pressure are newtons per meter squared. Again, you can see that you're taking a force and dividing by an area, so it's on a per unit. Most of the time, intensive properties are symbolized by lowercase variable names. Lowercase rho lowercase p is pressure. And I'll give you a longer list of them in a few minutes. Notice the temperature is the one that doesn't quite fit with that. Well, that should be lowercase. So we're going to use lowercase p for pressure. So we're always going to use a capital T for temperature, even though that's intensive.
Right? In predominantly capital letters.
Mm-hmm.
Could you add some sort of flourish to lowercase t?
Okay, I'll think about that.
Clear.
Yes, I think it'll be clear as but yes, it would be nice if I could be clear about that. I'll think about that, how to do that. Okay, so now that's intensive properties. Extensive properties are properties that are only defined over a finite amount of material. So if your system is this random thing, and we divide that up into, so let's say the system is S, and we divide that up into three sort of subsystems, S1, S2, and S3. Any extensive property, let's call it capital P of S, is equal to that extensive property for piece 1 plus that extensive property for piece 2 plus that extensive property for piece 3. Okay. And if you break it up into more, it has to keep adding up. So what are some things that work this way? Well, math has to work that way. And mass we're always going to write as a lowercase m. That is units of kilograms. And if you think about it in terms of the system and these subsystems, you know, the mass of big S has to equal the mass of this plus the mass of this plus the mass of this. The number of moles of material, that's lowercase n. It works for that. The number of moles in S1 plus in S2 plus in S3 gives you the total number of moles. Volume has to work this way. Area works this way. Usually, extensive properties are symbolized by uppercase letters. I guess the two counterexamples are the first two I gave. So that's not true for mass or moles. But I think in every other case in this class, extensive properties are going to be uppercase, intensive are going to be lowercase. So let me give you a list of some of these. So here are some extensive properties that we're going to see often. Mass M, volume, force, area, moles, and then some common intensive properties. So density, that's mass per volume. So kilograms per meters cubed. Specific volume, which is just the reciprocal of density. That's volume over mass. Pressure, lowercase p, that's force. Whoops. Force over area. So newtons per meter squared. Temperature. Okay, so let's go back to this idea of breaking up a system into little subsystems and think about. So we talked about how it works with mass, it works with moles, that the extensive property of the whole system is equal to the sum of the extensive properties of the subsystems, right? So let's think about it in terms of the intensive ones, and you see that it doesn't work. So imagine, I think the easiest way to imagine it is, imagine all of these having the same intensive properties, and think about what the intensive property of the whole thing would be. So say that all three of these regions have the same temperature, and the temperature of the whole system is just, you wouldn't say, so if all of these were at 100 Kelvin, then the whole system has a temperature of 100 Kelvin. It doesn't have a temperature of 300, Same with pressure. If you have the same pressure everywhere, you would say that the pressure of the overall system is the same as each one of these, not the sum of them. Okay. So you can always do that mental check whether something's intensive or extensive by thinking of breaking up the region and adding up the components. Yep.
When we're talking about these systems, we're talking about like a homogeneous system of gas.
Yes, in this case, yes. Okay, one thing to notice. Anytime you see an intensive property written with an overbar, so like for example, if you see a lowercase v with a bar over it, that means that you're calculating it per mole. Okay, so the unit that you're calculating per unit, and that unit is moles. So lowercase v with an overbar is volume per mole. Okay, so let's just quick go through temperature conversions, and then we can start talking about pressure. There are 4 temperature scales that we're going to use. There's Celsius and Fahrenheit. And then there's Kelvin and Rankine. Have you heard that word Rankine before? Do people say Rankine or Rankine? Rankine? Rankine. Google the pronunciation.
Yeah.
Will Siri tell me? Okay, so the idea is, you know what Celsius and Fahrenheit are. Kelvin is the Celsius scale with the 0 at absolute 0. And Rankine is the Fahrenheit scale with 0 at absolute 0. We just need enough conversions to go from any one of these to any other one. So you can do that with these 3 conversions. The temperature in Fahrenheit scale is equal to the temperature in the Rankine scale minus 459.67. So that's saying that Fahrenheit and Rankine have, 1 degree is the same in each one. They're just shifted a constant amount from each other. The Celsius temperature is equal to the Kelvin temperature, and for this one you don't use a degree symbol, you just write a capital K, minus 273.15. So again, you just see that shift. And then the Fahrenheit temperature. So the temperature in degrees Fahrenheit is equal to 9/5 of the temperature in Celsius plus 32. So with those three, you can get from any one to any other one. Yes, constantly. I don't know. I just want this to be in your notes. One thing to notice here is you have to be a little careful. This doesn't come up with any other kind of, well, it comes up in pressure, and we'll talk about that in a second. But for the most part, in dealing with units, you don't have to worry about what I'm going to say here because they all have the same zero. Things get screwy because these don't have the same zero. Okay, and here's what gets screwy. You need to know whether you're converting an instantaneous temperature or a change in temperature. The changes in temperature don't have the additive constants. And that's because if you're talking about, well, let me just give an example to show why that works, why it works that way. You know, the scale of the Celsius scale is the same scale as the Kelvin scale, right? So if you increase, if the temperature in a room increases 5 degrees Celsius, it also increases 5 degrees Kelvin. You know, it doesn't increase minus 278 degrees Kelvin, you know. And that's because a change in temperature, you know, a change in anything is the final property minus the original property. And on that final and that original that you're subtracting, you have the additive constant there. So those cancel out when you take that, when you do that subtraction. Okay. So if you're talking about changes in temperature, these conversions look like this. A change in temperature in degrees Fahrenheit is equal to a change in temperature in degrees Rankine. Change in temperature in degrees Celsius is equal to a change in temperature Kelvin, no degree symbol. And a change in temperature in degrees Fahrenheit is equal to 9/5 the change in temperature in degrees Celsius. Any questions about that? Anybody want to go through some quick example problems, or you feel pretty good about that? That's, yeah, okay. This is one of those times where, like, this happens to me all the time. You know, I teach like college physics, but I also teach like engineering classes, and so I get like, it's hard for me to, you know, what I need to do like in one class is very different than what I need to do in another class when I talk about the same topics. So that's it for temperature. So now we're going to talk about pressure. And you can talk about pressure in terms of solids, but you tend to talk about it more often when you're talking about fluids. So it's most applicable to fluids. And fluid is anything, so fluid. A substance that deforms continuously under the application of a constant shear force. Okay, so here's an example of what I mean. So if you, so over here, let's say we have like a swimming pool, and this is water. And you put a little raft on top of the water, and then you push it this way. Okay. What you're doing is you're applying a shearing force to this body of water that essentially has a force going this way applied by the ground and a force going this way applied by the raft. Okay. That shearing force is what makes this thing tend to, like if you start with this water a little bit later, that water would be here. You know what I mean? So if you applied, choose some amount of shearing force, when would the water stop this? Well, that's a stupid. I'm not gonna insult you by asking that. It's never gonna stop, right? If you push on the raft this way, it'll go until you run out of pool, right? It'll deform continuously under the application of that shear force. Not everything acts that way, because think about, like a solid block. And you apply forces in those two directions. It will deform, but eventually it'll get to a point, and no matter what it is, it's diamond or whatever, it's the stiffest thing you can find. It's going to deform a little, not very much, but then eventually it's going to get to a point where it's fighting that deformation enough that that same force doesn't deform it anymore. So a solid doesn't deform continuously. It deforms just depending on the stiffness of the material. Okay. Like a marshmallow would deform a lot before it stopped you, or it might break, but if it was a small force, a marshmallow would deform a little and then stop you. A diamond or block of steel would deform very little before it stopped you. What are the things that act this way? So this is a fluid. This isn't. And so the most common fluids that we're going to deal with are gases, liquids, and the weird thing that you get once you get past the critical temperature, supercritical fluids. It's kind of interesting philosophically or whatever that You know, all of these ideas are mathematical simplifications. Something that behaves as a solid under one set of loads will behave as a fluid under a different set of loads. And so you're always just picking what works best, you know. If you applied a shear force of 1 billion tons or whatever, a steel block would behave like a liquid, you know. Mhm. Yeah, right. Yeah, or like, yeah, like syrup. You can imagine very viscous fluids. They'll actually spring back into, like, if you apply a really small force and let go, they'll spring back into shape like a solid. So depending on the load, you treat them differently, you know. But you know, obviously, if you applied a big shear force, they behave like a liquid. There was, I know there was a geology professor who did this demonstration where I think it was meant to show how basically the material properties would change based on the loading time, how quickly a thing was loaded. You can see it actually if you go to like old historic sites, like at Fort Snelling. You see it if you've ever gone up into those buildings and you look through the glass. You can see everything's warped and thick down at the bottom. Like over a couple hundred years, the glass has actually dripped down towards the bottom, you know. But glass is a very stiff solid. But the demonstration this guy did was he took a big thing of silly putty and a big sledgehammer, and everyone put on goggles, hit it with the sledgehammer, and just shards of silly putty go everywhere. And you go and find them, and they're jagged and sharp like glass. You know, you with that really fast loading, it's a very brittle material. But you pick it up, and it's just a little shard of silly putty. You mush it, and you know. Yeah, yeah, we did it in the dorm. It was it worked. I don't know where you get silly putty anymore. That's true. Um, Here is a fact. Oh, no, I have to say what pressure is. So pressure um, is a force per area um, applied by the fluid uh, perpendicular to the fluid boundary. So, for example, if you have a round vessel with a fluid inside, the direction of the pressure that the fluid applies to the vessel walls. And the answer is at every point, that direction is perpendicular to the walls. So it's that direction there, there, there. Okay, so whenever something is subjected to a pressure, the direction of that pressure is out from the fluid towards the object and perpendicular to the surface. Okay. There are two important facts that we're going to use all the time about pressure. The first one is if you have a fluid that has these two properties. So if a fluid first is continuous, and second is at rest, then any 2 points in the fluid that are at the same height, so any 2 points in the fluid at the same height have the same pressure. The second one, it has the same two requirements. If a fluid, again, is continuous, so we're not talking about one jar with a gas inside and a totally separate jar over here. That doesn't work. They have to be together, continuous. And again, at rest, so the fluid's not moving around. Then, I need to draw a picture for this one. Okay, so this is the fluid. So let's call this location 1 and this location 2. And they're separated a height of h. It doesn't matter horizontally how far apart they are. Then the pressure at point 2 is equal to the pressure at point 1 plus rho g h. So that's how you calculate the pressure at the bottom of the ocean or whatever. You can use this formula to figure out, at the top of the ocean, the pressure is just the atmospheric pressure, and then you use density times 9.81 times the depth down to figure out what the pressure is below. I have these backwards. I guess it matters. It would work the way I wrote it before if you called positive height down, but that would be a crazy thing to do. Okay, so a thing like this is called a Venturi tube. You have a fluid flowing this direction through it. It speeds up here and is slower here and here. And if you measure the pressure in the fluid at those points, you have a high pressure here, let's say here, a low pressure here, and then a high pressure again here. So if these three are all at the same height, how does it work that, you don't have the same pressure on all three of those points at the same height? It's moving, and these are going to be really useful tools, but they don't apply if the thing's moving. Okay, there are two approaches for measuring pressure. The first one is a manometer. And that idea is used for measuring pressure in a contained vessel. So let's say here's our pressure vessel, and it's connected to a tube that goes down and then up. And you have a liquid in here. And you're trying to measure the pressure P in this bulb here. And the key is the difference in height there. This is open to the atmosphere. And so you know that, well, I guess let me just draw both of them and then we'll do the calculations. And the second approach is a barometer. That's for measuring the pressure in the atmosphere. And a barometer looks like a container holding a liquid. With a tube like this containing a liquid. So the liquid is at this height in the main part of the container, but it travels up the tube due to the atmospheric pressure pushing down on the top of the fluid. And this is based on this height h. Okay, so what's going on here? In the manometer, this is open to the atmosphere. So we know exactly what the pressure is at the, at the top of that contained fluid. That has to just be the atmospheric pressure. So if you know the atmospheric pressure, you know the fluid, you know the pressure there. What about in the other example? This is closed. And there's no air in there. This thing's evacuated. But the one thing you do have to be careful about is this fluid always is going to create vapor pressure. Okay, any fluid, like little by little, a little bit of it is always evaporating and then rejoining the water, and that evaporation is causing a vapor pressure. Okay, and the higher the temperature, the closer you get to the boiling point, the higher that vapor pressure goes. Okay. Well, we're going to approximate this as having zero vapor pressure, which means you want a fluid in there that's really far from its boiling point, because you want that vapor pressure to be really small. And that's why with the manometer, really any kind of fluid will work. With this, you use mercury, liquid mercury. And that's because liquid mercury has a boiling temperature at atmospheric pressure of like 600 some Celsius. And so there's a really low vapor pressure there. So in here, this vapor pressure is pretty close to zero, and we're just going to assume that it's zero. I assume that's the same reason why you use mercury in a like oral thermometer, or you used to. When I was a kid, I remember being at my grandma's house and like a thermometer broke, and we just set it on the table with her, and she like supervised us to be sure we were playing with the mercury carefully or whatever, like we're just pushing it around, Don't hit your head on the corner of the table while you play with this mercury. I'm editing that comment out of the video. Okay, so for doing calculations with these, both of them we're going to use this idea that no matter what the shape of the thing is, so say this is the container, if you have a pressure P1 there and a pressure P2 there, and P1 is equal to P2 plus rho GH. So here's an example problem. This one has to do with barometer. So let's say we have a barometric pressure of 550 millimeters of mercury. If you've ever seen, probably isn't used so much anymore, I'm not sure, but a lot of medical measurements of like blood pressure or any kind of pressure, at least used to be talked about in terms of millimeters of mercury. And it's because of this approach to, it's because of the way manometers were set up with that mercury inside, and you measure the height of it. So what's the atmospheric pressure in pascals? Given that the density of liquid mercury is, oh, I think I have that wrong. I think it should be 13,690, let's say, kilogram meters cubed. At room temperature, what's the density of liquid water? Anyone remember? In kilogram meters cubed? What? 1,000, yeah. It's 1 gram per centimeter cubed, I think. But anyway, so yeah, 1,000. So this is much, much denser than water. How about steel? How does it compare to, well, solid steel, I guess, is what I know. Solid steel is like about 7,000, somewhere around there. So that's a high density. Okay, so how are we going to calculate that? Well, we know that I draw this setup. So we know that this height is 0.55 meters if we're going to do it in SI units. We know that the pressure at this point is the atmospheric pressure. That's what we're trying to calculate. This fluid's at rest, and so we know that that pressure is the same as the pressure here. And what's the pressure at this point? It's about 0, right? So if this is P1 and this is P2, we know that P1 is equal to P2 plus rho GH. And so that's 0 plus 13,690 times 9.81 times 0.55. And I think you get about, can someone multiply that? I think it's like 74,000 or something. Okay, 73,000, what? 864, okay, pascals. And because the pressure P1 is equal to the atmospheric pressure, this is the atmospheric pressure. Anybody have a feel for how that compares to sea level atmospheric pressure? The pressure at sea level is about 1.01 times 10 to the fifth pascals. So, like 101,000 pascals. So this is, lower pressure than at sea level. Mm-hmm. Yeah, so I think, so density is kilograms over meters cubed. Acceleration of gravity is 9.81 meters per second squared. Height is meters. And so you end up with just meters in the denominator. Is that right? It should be in, oh, okay. And so, but we're talking, this should come out to be pressure. And so, so we come out with kilograms, and then times 1 over second squared, which is the same thing as kilograms meters per second squared over meters squared. And that's equal to newtons per meter squared. So it does work out. So that.
Wouldn't the first one be kilograms per meter?
Which one? With the stuff crossed out, this one?
Yeah, so you go over to the right,
Uh-huh.
with the top line being kilograms per meter. Times 1 over second squared.
You could do it that way. Oh, I didn't write the meters right. It doesn't work without those. Like that.
Yeah.
And then it works. Because, yes, then it works. What?
And then you just use one.
Yeah, exactly. Yep, right. By the way, that atmospheric pressure is, it's not really that low. There's a lot of mountains where the atmospheric pressure is lower than that. But so that's how you do the calculations with the barometer. And why don't we just stop there? So the idea with if you're using a manometer, you just have to remember that you're also adding on, so say the fluid goes up this high. This is the H you want. This is P1 and this is P2. You just have to remember that P1 in this case isn't just equal to rho GH. It's equal to the atmospheric pressure plus rho GH. Because P2 is the atmospheric pressure. Okay, so later today I'll put up the assigned problems. I have to look back over what they are, but I think there's like 11 of them, and I don't think it should take too long, so I think I'll probably just assign all of them. I'll make sure that we've covered all the stuff. Have a good weekend.